In this third quantum mechanics lecture, we're going to go a little bit more into what we mean by that quantum term by looking at quantum states. So we're going to look at how to build them and how to notate them a little bit. First, we will cover briefly what a state is and what we mean by it. And then we're going to look back at probability. Now, this is not going to be a lot of detail. This is going to be more about notation and how we write down states and how we can link that to probability, which is something we can measure. To briefly recap, what we covered in the first couple of lectures is the idea of a vector, and if it is off at a 45-degree angle there, it can be broken down into how much in the y direction and how much is in the x direction. And we can kind of build that up mathematically. Let's say there's a certain proportion in the x direction. Let's call that letter x. And that's going to be multiplied by the basis vector in the x direction. And then we're going to add it to a certain proportion, let's call it y, of the y basis vector. And that is going to equal e. That kind of equation is going to come back to us repeatedly. And in polarized light, we realize that, well, light has a particular direction to it. The field, the vector field, is oscillating in a particular direction, and we can control it using polarization filters. So before this polarization filter, it is at a particular angle, then all the energy in that direction is absorbed, leaving only the energy in that direction. And in the quantum mechanical model, we interpret that as the probability that a photon will pass, not necessarily the direction that it is actually oscillating in. So what is a state? We're chemists, we're immediately going to think of something like this. We're going to think of solids, liquids, and gases as states of matter, but that's a very specific and limited idea of what a state is. But it does help us understand what we could mean by a state more broadly. These things describe what the atoms or the molecules are doing. Whether are they sitting still? Are they moving around a lot? Are they moving around really fast? That's the difference between these three states. More broadly, though, we need to think about what could it mean in physics in general. And it is a much broader term here. And a state that we are talking about is all the information we need to describe a system. And that is literally all of it, the position of all the atoms, their speed, their direction, and so on. Now, in quantum mechanics, we can describe these by vectors and functions. They are mathematical tools. They are mathematical objects. They're not necessarily what the states are, but they are certainly what we can describe them with. And in quantum mechanics, in case you're doing some wider reading and you see these terms, we often talk about pure states or mixed states. So pure states would be, if we only have a basis, for instance, if everything was just in one direction, that would be a pure state. It can't be broken down into something else. But often, and more often than not, we can talk about mixed states. So these are complicated quantum states that can be described by multiple states, all added together. Now, we're going to build a state. And the notation we need to talk about is this, the Greek letter psi, or psi. I'm not going to embarrass myself by trying to do the Greek pronunciation properly throughout this. I will just call it psi. And this is a symbol that we will see repeatedly. And if you see it, it just means quantum state. It is a mathematical object, so it is going to be equal to something. It represents a particular equation, but what that is, we don't necessarily care about. We may, when we're doing some actual pen and paper maths a bit later on, look at what it's equal to, but for now, it's just a quantum state. It may be represented by other quantum states as well. So let's apply this to the polarized light model. So if we have polarized light coming towards us through some filters, we can see that it's off at a 45-degree angle after the first one, then it hits the second filter, and it's all truncated into one direction. And again, in the quantum mechanical sense, that is a probability that light will pass through rather than a reduction in the field. And let's apply some state notation to it. Before that second filter, we have capital letter psi. That is a quantum state representing light going at a 45-degree angle. After that filter, we have a different quantum state. I'm going to use the lowercase psi for this with a subscript saying pass. So that is saying that it is in the state that can pass through the polarization filter. Any particle in that state can pass through the filter. But before it, what is that big psi equal to? It's got to be equal to something else. We can put a bit more detail in there. And, well, we can just make a superposition. So this is a linear combination of two states, so it's mixed between a state that could pass and a state that is blocked. So we have two states mixed together. Now this is not the same thing as them being the two different states at the same time, and it's not that half the molecules are in one state and half the molecules are in the other state, or half the photons are in one state and half are in the other. It's a state that can be described by a combination of these two. But that equation down there is not the end of the story. We need those coefficients to describe how much of one is in each. And these are going to be equal when we're at 45 degrees. They're not going to be equal to 0.5, as we'll see shortly. But those are coefficients that we need to know about. So that's how we build a quantum state. We've got big psi is equal to two other states added together, multiplied by two coefficients. So we can work out what these A's and B's will be simply by remembering that, well, we're at an angle here with polarized light, so there must be a way of working out each of these individual magnitudes from trigonometry. So we can work it out as sine theta and cosine theta, and if this angle is 45 degrees, then sine and cosine of these are both equal to each other, and is equal to 1 over root 2. So A and B in that equation, if it's at 45 degrees, would be 1 over root 2. That's a fairly straightforward quantum state equation. So before we move on to probability, let's just recap to what a general looking equation will look like. We'll have our quantum state psi, big capital letter, and we see it's going to be equal to two other states multiplied by two coefficients. And underneath it, there is a slightly different notation. It's this angled bracket and vertical line, and that is called a ket. We're not going to go too much into this, but it is going to be useful when we talk about spins, and it's useful in next term's course on formal quantum mechanics when we need to use it a bit more. So I'm just going to leave it here to show you that it exists. If you see these symbols when doing any wider reading or elsewhere, this also means quantum state. It means exactly the same thing, just the notation is different and the concepts we use to underpin it are a slightly different thing. But the short answer is that it does mean the exact same thing as psi without the angled brackets. So let's build a state a bit more complicated. Well, if we want to relate it to probability, well, we need to know what's the probability of finding A or B when we measure it. These are the only two states that can describe the main state here. So if we were to measure it, we will find one or the other. You know, like when passing through a polarization filter, light is blocked or it passes through. There is no other option there. And the probability of both of those must add up to 1. So 1 over root 2 plus 1 over root 2 is clearly less than 1. So that's not going to work here. Well, so we need to square these instead. And then we find out that it's actually equal to 1. So if we square those coefficients, we get the probability of finding that state. And we don't necessarily need to leave it at just two states. We can add in a third. How we then work out those coefficients becomes a little bit more complicated. We need to start thinking in three-dimensional coordinates. And if you add a fourth state in, it'll get more complicated still. But these things can be modular. We can just build on. As long as all of these coefficients, a squared plus b squared plus c squared plus d squared, all add up to 1, this can be valid. We can mix the states together, we can mix and match them in different amounts, and the odds of us finding a particular pure state when we measure it can be found by squaring those coefficients. Right, so just to recap the idea of quantum states now. A state is all the information we know about a system. There are some interesting philosophical ramifications of that when it comes to quantum mechanics, because that information is like limited slightly. But in quantum mechanics, states can be mixed. So this means that we can take states and we can mix them together by adding them, multiplying them by different numbers, and we can build more complicated states out of that. And they're all represented by equations, so we can add them together and we can relate it to probability by squaring the coefficients. So if we have a complicated mixed state and we measure it, we will find a pure state with a probability of those coefficients squared.